Hello guys, welcome back to my Black-Scholes derivation video series. In the previous video, we discussed the general movement of a financial asset and how to model that as a mathematical equation in both a general form and a differential form. So just to recap those, we have the general movement of a financial asset. And we concluded that we can represent it in differential form as such. We have ds is equal to s times mu dt. And then in standard form, we have our s as a function of time is going to be equal to our initial stock price times e to the power of mu t, such that we have s0 and mu, which we can choose. So these can be calibrated depending on the stock or the system that we're interested in analyzing. And to go off of that, I want to draw a little picture representing this. So this is going to be our stock price as a function of time, our initial time, and this is going to be our time axis. We can choose an initial stock price at the time that we're interested to start our analyzation, and we will have some kind of geometric drift. So as stated before, if we have a mean returns constant, which is greater than 0, we'll have a positive drift, and if we have a mean returns constant less than 0, we'll have a negative drift with an asymptote at s is equal to 0, which will adhere to our stock price range, which must fall in the range of 0 to infinity. Cool. Now, the way stock prices actually look in the real world is going to be somewhat random, and we'll talk about what random really means. So it's going to look something like this, and it's going to follow some kind of drift. Something like that. So this could be our true S1 of t, and this could be our true S2 of t. And we're interested in this residual, if you will, and what the behavior of the residual really is. And what we choose to represent it as is a random variable, because there's no way to actually model these kinds of inherently random movements in a deterministic form, right? So we're going to say this is just random. Now, what kind of randomness is present in the residuals, right? So that's another interesting question. So to answer that, I'll start with a small little example. Let's say my stock price is trading at $100. And let's say with some kind of a random movement, it can go up to 101, or it can go up to 99, or sorry, down to 99. Now, another random index that I'll take is, let's say it goes down to $9 and it goes up to $1,001. So we know that just by looking at the stock market that these have a higher probability of happening. And let's say these are the stock prices at S of 1. And the time increment, let's say, is in days. So in one day, if we have a stock trading at $100, it is way more likely to either go up to 101, for example, or go down to 99, and somewhere in between, rather than it going all the way up to 1,001 or down to $9, right? So these two cases have low probability. This one also has a low probability. So if I were to represent this as frequency, if you will, or a probability density function, right? I could represent it as such. If I have a stock price, let's say my S0 is equal to 100, right? I'm expected to get somewhere around that same stock price. So my density function would almost look like this. And the higher this point on the curve is, the greater my probability is, right? So somewhere around 100, let's say 99 and 101 have a pretty high probability of happening, and points around the middle also have a high probability of happening. And as I deviate further and as I go down to, let's say, $9, and using the same example, $1,001, there's a very low probability of these events actually happening, almost close to zero. And this is essentially a normal distribution. So essentially what we're going to assume with all these random points is that they follow somewhat of a Gaussian or normal distribution. Even though they are random, the type of random variable that they are is a normal distribution. Cool. So mathematically, I can just add this into my differential equation. So I have ds is equal to mu s dt, which is going to be our drift term, or our general movement of the stock. And then at every increment that we choose to move forward in our time progression, we're going to add an infinitesimally small random shock, which I'll call dB. So this is going to be our shock. And our B is going to be our Brownian motion. And B is a function of time. And this is essentially where we're going to include the notion of a normally distributed random variable as a function of time. And essentially, we will be adding this aspect back into our general model to fully represent our financial asset in the way it appears in the real world. So let's define what Brownian motion is. So the definition of Brownian motion actually comes from a theorem, which I will not be proving in this video. It is quite an extensive proof, which requires a very vast mathematical knowledge. So instead of deriving it, I'll just state it. And here's how this theorem goes. So there exists a probability distribution over the set of continuous functions with the domain R, all real numbers, which is greater than 0, mapped to the set of all real numbers, which defines our Brownian motion as a function of time. Okay, cool. Now, we have three properties that will define this function. So the first property is as follows. We're going to state that the probability that our Brownian motion at time 0 is going to be equal to 0. And this has a probability of 1. So this essentially states that our Brownian motion is going to start at time 0 and will be 0 at time 0. And that has a certain probability. Our second property is as follows. For all 0 is less than or equal to s is less than or equal to t, our Brownian motion at t minus our Brownian motion at s is going to follow a normal distribution with mean 0 and variance t minus s. So this right here is going to be our mean in our normal distribution function, and this is going to be our variance. If you don't know much about probability and statistics, I recommend looking at some other YouTube videos. I will not be going over the basics of probability and stats in this video series. But the amount of probability and stats that I'm going to be covering is going to be quite minimal. So this is essentially what is going to be represented from our Brownian motion at time t minus our Brownian motion at time s. Now, another way of writing this, which might be a little bit more important, as we'll see in the coming videos, is as follows. We can say the square root of t minus s, which is essentially our standard deviation, our one standard deviation times our normal distribution from 0 with a variance of 1. So these two are equal to each other. And now we have our third and final property, which essentially states if s and I, ti, are non-overlapping, then b ti minus b of si is independent. So this is going to be our theorem that represents and mathematically defines Brownian motion. I'll be going over a graphical representation of this and what it actually means from an intuitive standpoint in the next video.